We're going to talk about Markovnikov addition of a hydrogen halide to an alkene. Now, as we talked about previously, you can draw the alkene with wedges and dashes, but in this particular reaction, it's not going to matter if you do or don't, and the reason for that is because, again, there's a carbocation formed in this reaction. Whenever you form a carbocation, it doesn't really matter if you draw the wedges or the dashes. But in this type of reaction, you will have a hydrogen halide. The one I use most often is HBr, but this will work with HI, HBr, HCl, and potentially even HF. And we usually do this so that it is concentrated. You don't want your solvent to be an electron pair donor, so usually we use an organic solvent like chloroform and heat. You could also use something like methylene chloride, which is CH2, Cl2. You could use benzene, pretty much anything. Just make sure it's not an alcohol or an amine derivative, because those are potential nucleophiles. And then I'm just going to add some hydrogens on here and a methyl group so that we have some differences to talk about. Since we are talking about a Markovnikov addition, this is a regioselective reaction, which means that the hydrogen will add to the less substituted carbon of the double bond, and the halogen will add to the more substituted carbon of the double bond. In order to make this reaction work, we've got to understand some chemical principles. HBr is a strong acid, and as a strong acid, it is a proton donor. And this you can find out through the pKa's on your pKa chart. And so if this bond were to break, bromine would take those electrons, because bromine is very electronegative in comparison to the hydrogen. And that means you've got a proton available. Now, as you can see, I'm not drawing my alkene with the wedges and the dashes because it won't matter for this particular reaction. But if you've got a proton available in the solution, it needs an electron pair to come pick it up. Now, you don't have an electronegative atom over here on the alkene side. There isn't one. There is no electron pair donor. But you do have a pi bond. Now, pi electrons are at a higher potential energy than electrons in sigma bonds. And so if you are going to break a bond in order to get an electron pair, you're going to break the pi bond because it's a weaker bond. And we will use that pair of electrons to pick up the proton. And you want to draw it from the electrons, not from the atoms, because it's the electrons that are picking up the proton. Now, out of these two carbons, since we're sharing those electrons between them, we need to decide which of these two carbons is actually going to make the bond to the hydrogen. And this will be the primary carbon, because I would rather have a secondary carbocation, because secondary carbocations are more stable than primary carbocations. And we're going to draw what that looks like here. So we're going to add that proton, which we've done here, to the primary carbon. As a result of that, you make a secondary carbocation. Now, carbocations are highly unstable, so this was the slow step of the reaction. It's the step that takes the longest amount of time because it's the hard step. Now, carbocations are stabilized by induction and hyperconjugation of the neighboring groups. And in this case, since it's a secondary one, you should be thinking about potential shifts through hydride shifts or methyl shifts to more stable tertiary carbocations. In this case, you can't do either, because if you did do a shift, you'd have to do a hydride shift, and you would end up with a primary carbocation, which is less stable than the tertiary carbocation, or sorry, than the secondary carbocation. So there is not going to be any shift. So at that point, you're trying to stabilize the carbocation, and you need a nucleophile. Well, the solvent is of no help, because we made sure we chose a solvent that was not an electron pair donor. But the bromide is, and it's a very good nucleophile for a couple of reasons. Number one, it has a lone pair. Number two, it has a negative charge. And number three, it's a very large atom. And number four, it's a weak base, so it's got everything going for it. It's a fantastic nucleophile. And what it will do is it will donate some of its lone pair electrons to this carbocation. And as a result of that, you will make your alkyl halide. This reaction proceeds in exactly the same manner as the Markovnikov addition of water to an alkene. The only difference between these two mechanisms is which one is the nucleophile. For the addition of HBr, bromide is the nucleophile. For the addition of water, water is the nucleophile. And based on which group is the nucleophile determines if you're making an alkyl halide or an alcohol. But it requires basically the exact same mechanism.